Welcome to another lesson. Today, this lesson will be focused on electromagnets and also electromagnetic induction. So we're going to learn a lot of things as it pertains to electromagnets. We want to see how electromagnets are used in our daily lives and so forth. So let's get straight into it. Now it says an electromagnet make use of electromagnetic effect of a current carrying wire. It says when a current flows through a solenoid, a magnetic field is produced. When a ferromagnetic material such as iron is introduced inside of the solenoid, there is a concentration of magnetic field, and it says that the result in this are in an increase. The result is that there is an increase in the magnetic flux density. So when we talk about electromagnets, as the word suggests, elect, which speaks to electricity, right? And then now, through means of electricity, we can create a magnetic field. So this is basically what is happening. So whenever we have a solenoid, and we know by now that a solenoid is a coil of wire wrapped, in a spiral way. Now, if some amount of current is applied to that piece of solenoid, what you would observe is that this solenoid is going to become magnetized. And by becoming magnetized, we now form what we call an electromagnet. So in a sense, it's a magnet, but this magnet is as a result of the flow of electricity through a solenoid. And we're going to look at how it works eventually. But one of the things that I want for us to understand about electromagnets, right, is that whenever we are constructing an electromagnet, and one of the main type of electromagnets that you will come across is what we call a solenoid. Now, in the construction of the electromagnet, we generally use soft iron. So there are different types of iron. You have irons that are hard and you have irons that are soft. Now, the lovely thing about using soft iron to make a electromagnet is because it has what we call high permeability. Now, if you can recall anything about permeability, permeability speaks to the ease through which a magnetic field can pass through a material. So the higher the permeability is, it means that it's the more easily a magnetic field is able to pass through that particular material, and so soft iron can allow that to happen. Not only that, when it comes down to using a soft iron, it makes it easy to become magnetized and also becomes easily demagnetized. To become magnetized is when you make the metal becomes magnetic, right? And there are several ways in which we can actually make a soft iron becomes magnetic. One method is by the electrical means. Another method is by actually striking the soft iron across a permanent magnet. So imagine that I have a big magnet here, and by taking the soft iron, so this is the soft iron, and if I were to go ahead and move it back and forth over the permanent magnet, which is this is a permanent magnet, then you will realize that this magnet will become magnetized. But the beautiful thing about soft iron is that it does not become a permanent magnet, right? So what we say is that it becomes demagnetized over time. So once you remove the the permanent magnet, so if we remove the permanent magnet and we now have the soft iron by itself that had become magnetized, over time it's going to lose its magnetic properties, right? And that is just due to the construction of the soft irons. All right. Now, what I can say next is that when it comes on to soft iron, it is able to concentrate um, the magnetic field lines, right? So that's a beautiful thing about the soft iron, right? Because what you see, let's imagine that this is the soft iron before it becomes magnetized. In the process of it becoming, before it becomes magnetized, there are some things that we call domains that are inside of the material or inside of the metal. Now, with these domains, they are in random positions, meaning that these are how the domains look before it becomes magnetized. They are going in random positions. But as soon as we magnetize the material, what we see is that those domains, they line up perfectly in one direction, so to speak. So let's imagine that all of them are going to be lined up like this. So that is what is taking place when we basically create a soft iron. We allow the domains to become in moving in one direction, right? So this is why we're saying here that the electric field lines are concentrated. So you can imagine if this becomes a magnet, then you can expect that it's going to have electric field lines. Well, not electric field line, magnetic field lines moving from the north into the south. So this would be the north. So let me just clarify that. From north to south. So that's how magnetic field lines move from north, right, into the south. So that is basically what is happening here, right? Now, the thing about this is that once we remove the permanent magnet, what you will see that over time, those domains inside of the soft iron, they then go back into their random position. So in a sense, that is how it loses its magnetization. They then go back into some random position. And of course, if they're in random position, it means therefore that then, you know, we can just look at it to say that the material is no longer magnetized because the domains are moving in all different directions. Okay. Now, another thing that we want to just recall here, as it pertains to the magnetic flux density for a solenoid, we use this particular equation here to measure the magnetic flux density of a solenoid. So imagine that we have a solenoid looking like this for argument's sake, and I want to measure the magnetic field that is generated when when um when this is when that particular solenoid is inside a magnetic field. I can use this equation to say B. We use B for magnetic field, so this B means magnetic field or magnetic flux density, I should say, magnetic flux density. And that just speaks to the same thing as what we call the magnetic field strength. Magnetic field strength. So if you see these things, it's really the same thing that we're talking about. Now, mu, as you would have heard probably in more than likely the previous lesson, mu speaks to the permeability of the material, and that is a constant, right? Times the number of turns, right? Times the number of turns times the length of the what we call it now, of the solenoid, all right? So we could actually find out the magnetic flux density, right? It says that when a ferromagnetic material such as iron is introduced inside an air-filled solenoid, the magnetic flux density increases significantly. And it says that this can be compared with the effect of inserting a dielectric inside of the plate of an air-filled capacitor. Now, what we're actually saying here is that in most cases, the solenoid can inside of the solenoid, it's almost like you looking. Imagine that you are looking from a aerial view position, right? In between here, in between the solenoid, we're seeing that we can actually put a type of material inside of it. So this part here in between, we can actually put something in between here to just take in that space. Now we call those type of materials ferromagnetic materials, and they are basically materials that can become magnetized easily. We can also call those the soft irons really. If we go ahead and put a soft iron in between the what we call it now, the solenoid in between it, then what you would observe is that the magnetic flux density will increase significantly, meaning that the solenoid will now become a stronger magnet at the end of the day, a stronger electromagnetic, um, well, a stronger electromagnet, right? It will become a much stronger electromagnet. When we think about capacitors, we know that capacitors are basically, you know, let me see how best I can draw a capacitor here, right? We have what we call parallel plate capacitors. So imagine that this is my capacitor, right? Where I have this plate right here. This is the first plate. This is the bottom plate. Now, in between here, so as a matter of fact, let's make this plate becomes positive and this one becomes negative. As we know, um, charge moves from positive to negative. So this is essentially what is happening when you have this is a capacitor, right? By the way, parallel plate capacitor. We're just making a little bit of distinction here. Now, at this very moment, inside of my capacitor, it is air is located inside of my capacitor, air-filled capacitor, right? Prior to me putting in the ferromagnetic inside of the solenoid here, there was basically air inside of it, right? Now, what we're saying here is that if we were to incorporate or include what we call a dielectric inside of the or in between the plates. So if I were to put a dielectric of some different type of material, maybe let me see if I can think about a dielectric quickly. Um, wow, I can't think of any right now in terms of the material. For argument's sake, let's just say lead for argument's sake. I'm not saying that lead is actual um, dielectric, but let's just imagine that is it. Now, based on the type of dielectric that I incorporate in or put in between the plates, then what you would realize is that different dielectric in between the plates will allow the capacitor to basically store more charge inside of it. And a capacitor is something that stores charge. So by way of increasing the dielectric inside here, the dielectric enables the capacitor to store more charge for a longer period of time. So it's the same thing when it comes down to the solenoid. If the solenoid has a ferromagnetic inside of it, then what you essentially see is that solenoid is going to become a much stronger electromagnet. Now, there are different uses of electromagnets, and we must be able to can identify the uses of electromagnets in different industries and see a little bit as to how they work. So one of the main type of electromagnets that you have seen but have not seen it in a sense is when you're using a magnetic or when you go into like the grocery store and all of those things, right? Some of the times that door automatically shuts by itself. You have some doors that will slide open automatically and all of that. So in some of these cases, they're using the mechanism of electromagnets. If you have ever been to Western Union and those bank areas where you have to probably try to be keeping out criminals and all of that, then you would see that when those doors are locked, right? Somebody over the counter would have to press a button so that the door can essentially become open. What is really happening is that when the door is locked, right, it's basically using electromagnet or electromagnetism to lock the door together. So it's like you're taking a metal and a magnet and locking them together using a very strong force. Now, whenever you what would I say now? Whenever you want the door to open, you have to cut the power from the electromagnet. So you basically what would I say now? Um, so once you want the door to open, you have to cut the power from the electromagnet so that the electromagnet no longer becomes magnetized. And if it does not become magnetized, or if you cut the power source, then that is how you're now able to open the door. All right. So that is typically one use of magnetic door locks in buildings, so to speak, by just using electromagnets and metals to kind of close the doors, so to speak. All right. So to open it, you have to press a button to essentially de-energize the electromagnet, which is just cutting the circuit, meaning that you're taking away current from flowing to the electromagnet to allow it to become demagnetized. And as we said, when it comes down to electromagnets, we generally use soft irons because you want it to lose its magnetic or the magnetic property as soon as possible. So that is one of the reasons why we say we use soft iron, because it can be easily magnetized and can also be easily demagnetized. So as soon as you shut the door, then the circuit goes back in its original state, where now the electromagnet now becomes, or becomes magnetized again, and so the door will end up being locked. And of course, if you need it to open again, you need to press the button. Another type of device that you will see us talking about, or that you should know how it works, is what we call a relay, right? Now, this works a lot in motor cars and so forth. One of the things that you must understand is that whenever you turn over the ignition in a car, for those who are interested in cars and in the future you're going to drive a car and all of that, what we really do is that by turning over the key to the ignition, what you're essentially doing, you're allowing what we call a relay to become magnetized, and by becoming magnetized, that relay will allow some other type of material, some other magnetic material, to basically trigger on, or to trigger a switch to turn on, basically. I'm going to show you what I mean. So once this circuit is closed, then I think let me see something here. Now, as you can see, there's an open circuit right here. In electronics, you will realize that this is what we mean by an open circuit, right? So this is an open circuit. Open, my bad. Not, yeah, we can call it an open circuit. We can call it an open switch. So we can call it an open switch. Now, once we close that switch, we can expect current to flow. So that is what is happening here. So once we close this switch, what you're going to see is that current is going to flow all the way around this solenoid. And of course, because current is flowing around the solenoid, it's going to become magnetized. And by becoming magnetized, it is now a magnet, an electromagnet. And of course, there's soft iron inside of it, which is basically that thing that will aid with making this solenoid becomes more magnetic. What you're going to see occurring is that when the magnet here becomes magnetized, it's going to attract this piece of metal right here. So this piece of metal here is going to attract it. So let's look at what is happening here. So the metal is going to essentially move down. It's going to move down further, and by moving further down, because it is now magnetized, you can see that this metal here that was initially here is now touching against this contact, right? So whenever that occurs, you can now see that current will be able to flow through this wire and can actually do something else. So the way how car starts, it uses the same procedure. So when you turn over the key in the engine, right? I wish I had the picture to show you. But whenever you turn over the key, what you're actually doing is that you're causing this solenoid to become magnetized. And when this solenoid becomes magnetized, it allows this contact to move down to the magnet so that it can touch it right here, right? So imagine that this is now your new contact. It's touching against this other contact, which just means that current can now flow to the other part of the engine to tell it to turn on and start. You understand? So that is essentially kind of what is happening there when it comes down to electromagnets. I mean, this is not only used in cars, but it's also used in radios and also what we call it now, how the school bell actually works. So the school bell relies on a relay system so that it can move, it can turn on and off and all of that, or it can actually make sounds. So that's essentially what is happening here, guys, and we must know this information. All right. Now we move on to a lovely part of physics that speaks to what we call electromagnetic induction. And I must say something here. This is a powerful, content, and not only content, but principles that we have adapted to use over time. You understand? Now, when we think about a wind turbine, right? You might be wondering how it works. How does a wind turbine generate energy or generate electricity? What we are going to learn in this lesson is that we can actually create voltage, or we can actually create current by way of inducing what we call an electromagnet, right? Or what we generally say an electromagnetic induction. I want to show you what the scientists, man like Oersted and Faraday, when they were doing some amount of work as it pertains to this. Let me just show you what the simulation looks like. So here we have, a magnet right here, and here we have a coil, basically a solenoid, so to speak, and there's a light bulb attached to it. Now, when Faraday was experimenting with, one of the things that Faraday thought about, let me just give you a brief history of what happened. So a man by the name of Oersted was able to realize that whenever current is flowing through a wire, right, there is a magnetic field associated with the wire. Good. Now, so Faraday accepted that information. He agreed, but then he went ahead and said, "Hey, you know that? Let's just imagine something here. What if I have a wire, right, and I bring a magnetic field towards the wire? Let me observe what would happen." And when he did such a thing, when he asked such a question and did it, it was mind-boggling. It created a lot of, what would I say? A lot of results. Let me just put it as such. Because what we're going to see now is what Faraday did years ago, where he took a magnet and brought it closer to a coil, right? And when he brought it towards the coil, he realized that there was a voltage that was essentially being given off. You understand? Or in essence, you could say that current was flowing through the coil. Mind you, when you look at this, there's no current source associated. Sorry, there's no current source associated with this. You're just seeing a piece of wire wrapped around in a coil, and you have a light bulb attached to it. But now, when Faraday looked at this, he said, "Hey, let me just take the magnet and push it inside of the coil." And while doing that, he was now able to see that an EMF was induced in the wire. And with his understanding of what was taking place here, he was able to come to a conclusion, or to see that the faster the magnet moves in and out of the coil, it's the brighter or the more EMF, electromotive force, that would be produced. So we can also observe it. So if we move the thing very fast back and forth inside of the coil, then essentially what you're seeing is that there's more um, current flowing and more voltage being supplied to the system, or being created. So this is revolutionary, where we now can see that we don't always need a battery or actual alternating or direct current to actually make current in a sense. We can use a magnet that is thrust in and out of a piece of wire, right? And with this now, we are now able to catapult this knowledge to see how, how wind turbines work. Not only how wind turbines work, but also to see how any particular generator, how they actually work. You understand? So we're going to look at it. We're going to look at it very extensively, right? And understand what's going on here. So let's look at it. So the whole reason why we call it magnetic induction is because we are inducing a magnetic field inside of a wire, and as a result of that, we're seeing that there will be a voltage produced. So let's look at this here. It says, let's consider a solenoid attached to a sensitive galvanometer. A galvanometer is just like a voltmeter, where it's going to read the voltage. All right. It says that as the bar magnet is slowly moved towards the coil, a deflection is seen on the galvanometer. If the motion of the magnet stops, it says here that the deflection goes to zero as the magnet passes through the coil and exits. On the other side, a deflection in the opposite direction is seen on the galvanometer. And I think you guys were able to see that. Let's just look at this. Let's use a galvanometer here. Now, let's observe the direction of the needle. So when I bring my North Pole in, I realize that this wire, well, not wire, but the needle went towards the left, right? It goes towards the left. And we're going to look at why that occurred. Why did that happen? Why didn't it move to this side? Why didn't it move towards the positive side? Now, when I push it through the other side now, so we're going back now, I realize, let me just check again because I want to get it properly. Okay. So yeah, so by going towards the left, we're realizing that our our EMF is going towards the right, meaning that the needle is going towards this side. So look at it, right? It's going towards that side. So there are several things that are occurring right here, and we're going to look at it in step-by-step process. Now, so that was one experiment that we could have done right there, and then to look at the whole aspect of induced EMF. But we could actually do it from another standpoint. right? So in this one, we use a magnet. We use a magnet and use the magnet to induce in a coil. Now for this type of experiment, it's the same kind of electromagnetic induction. What we're really doing here is that this now is, as you can see, there is a voltage applied here. There's a voltage applied here, so you can expect that this coil A, this coil is going to be your coil that is going to have the magnetic field around it, right? And if I take coil B and move it towards coil A, then what I'm going to essentially observe is that there's going to be a deflection in this coil, right? So once I'm inducing coil A into, coil B rather, towards coil A, then automatically there's going to be an EMF that is going to be given off here on this thing, right? Now you're going to hear me talking about Lenz's law very soon, but we can just read what it says here. It says that when coil A is moved towards coil B, right, the current induced must oppose this change, and this is what Lenz's law states, which just tells us that the coil must repel. The coil must therefore repel. So the thing about the electromagnetic induction is that, one of the things that we must understand is that things don't like to change. Meaning that in life, when you check out things in life, a poor man, will, for the most part, I'm not saying that he will always want to be poor, but in most cases, a poor man will always remain poor if he does not do something about his poorness. When it comes down to our wires right here, what we're seeing is that the wire is opposing the change that is coming towards it. It is like saying it's like a rich man coming to a poor man and say, "Hey, I can show you the way of getting rich," and the poor man, which is the coil, is rejecting that information. So what Lenz was able to see was that whenever we bring, I'm going to use this example, whenever we bring a north pole towards the coil, what the coil is going to do, it's going to essentially create a magnetic field that will oppose the change going towards it. Hence, that is the reason why the direction was able to change, meaning that the direction of the current that we looked at on the galvanometer would have changed to a particular direction. Now, we can use, obviously, I think it's the right hand grip rule. Now, here we are. We're just discussing Lenz's law right now. We're going to talk about it a little bit more. But here's what is happening. So we're saying Lenz's law is saying that, or Lenz is saying that whenever we take coil A and move it towards, or coil B and move it towards coil A, the current induced must oppose this change. All right. So here we have. All right. I'll soon come back to that. Let me see here. So here we have our north pole going towards the coil. What we're essentially saying is that there will be an induced current inside of the coil. Now, that induced current must flow in a direction so that it creates a magnetic field that will repel the magnetic force coming towards it. So at the end of the day, right here, so this solenoid must create a north pole to repel the magnetic field coming towards it. Right? So that's one of the key things. So if you know what pole is going towards it, then you can essentially know what pole will be at the coil. So if I have N going towards my coil, then automatically my coil is going to basically create a north pole right in front, because its tendency is to repel each other. But now we want to see the direction of the current. We want to see where the direction of the current is going to go. So let's look at this. So if we remember the right hand grip rule, the right hand grip rule for solenoids. As it pertains to solenoids, there is a specific way how we do it. So we say that your thumb will show the direction of the magnetic field, and your four fingers will essentially show the direction of the induced current. So let's look at it now. So imagine, take your right hand, open up your right hand. Your thumb is going to show you the direction of the magnetic field. Your four fingers, the way how they curl over into your palm, that will show you how the induced current is moving. So this is what we're seeing. Because you know that there's a north pole coming towards the coil, then you automatically know that the coil is going to present a north pole at this position. So you know that your direction of your magnetic field from the coil is going that way. So from that information, you can now see that the current is flowing over and coming down like this. So the current is coming down like this, it's coming over like this. So essentially, current is flowing all the way over, coming on like this. So hence the reason why you will see that the needle is moving towards this side, because of the fact that the current is flowing over. It's coming over like this. The current is coming over. So let me see if I can draw another solenoid, right? So the current is coming over like this each time. Coming over like this each time, right? That's essentially what is happening there. It's a little bit hard to show, but what you have to note and to remember is your right hand grip rule. And once you know your right hand grip rule, then you will see that this is the way how the current is flowing. It's coming over on this side. It's coming from behind and over, right? Coming from behind and over. And that is the reason why the deflection is on this side. We can use the simulation again to just look at it. We can use the simulation. So these are my particles. I want to observe where the particles are moving towards. That is a bit hard to see, but I think my particles are going over like this. They are coming over like this. I want to see if I can change the direction of my magnet, just to make life a little bit more easier. I'm trying to see if I can change the direction. Right. I doubt I'll be able to change the direction of the magnet, because I wanted to show you from the standpoint to say, all right, let's see, yeah, flip polarity. So I just did it just now, flip polarity. So this is what we were looking at in the previous thing, right, on the slide. So by way of taking the north pole and bringing it over on this side, let me see. All right, so it's not completely showing what I want. But what I want you to see, let's do it again. I want you to see that the current is flowing, how the direction of the current is flowing. So let's look at it. If we were to consider the right hand, let me see right here. Yeah, I'm just trying to just see what's going on here. All right, this might be a little bit challenging. I don't know what's happening with this, but at the end of the day, what we're literally saying is that the coil is going to generate a a um a repulsive force that will show us a direction, right? That will be going in the opposite direction. Let me just go back here and just see what's going on, right? So it says that the direction of the current induced in B is therefore in the opposite direction of the current in A. So if the current in A is going down like this, right? Then what we're saying on this side is that that is going to be the reverse, right? But we're going to look more on this further on. But we just want to put in a little bit more information here and there as it pertains to magnetic, you know, just to just understand a little bit more, because we're going to use this information a little bit more. It talks about magnetic flux, right? You'll hear us using this terminology and you must know how to define it. So magnetic flux is the number of magnetic field lines passing through a particular area, right? It can therefore be defined by as the product of the magnetic flux density and the area normal to the line of magnetic flux. The SI unit for magnetic flux is what we call Weber, and we use W, capital W, B to as a shortening for the unit. So this is essentially what the equation says, that magnetic flux, right? How we find the magnetic flux is by taking the magnetic field or magnetic flux density and multiplying it by the area through which the magnetic field lines are passing through. So essentially, magnetic flux is basically the number of field lines that are passing through a particular area. Imagine that we have this area of material, and we have field lines that are passing through, going on this side, field lines that are passing through, going on that side. Now, if I want to find my magnetic flux, I need to know the area through which the magnetic field lines are passing through. Also, I need to know the magnetic field strength of the field lines that are passing through. So at the end of the day, right, psi, this symbol here, I think they call it psi. Psi is equal to, and it's psi. I mean, almost like you're saying psi, but it's psi. Psi is equal to, which is the same thing as our magnetic flux, is equal to the magnetic field line times the area. This is when the magnetic field lines are passing through at a 90-degree angle. So what I drew here is not completely the accurate thing, right? I wish I had it more. So imagine that this is the area of material, right? I mean, it's from a different side view. It's from a side view, right? And you have these field lines passing through it. This is when you are actually measuring the overall, magnetic flux, right? So if you know the area that the field lines are passing through, so this would be the area of the material, and of course, the field lines will have its magnetic field lines, magnetic flux density. So having said that, we can find the magnetic flux. Now it says that if our magnetic flux lines are not perfectly normal to the area, then we can adjust our formula a bit by saying that our magnetic flux is equal to the magnetic flux density, right, times the area times cos of the angle. So in most cases, the magnetic field lines, depending on, so if this thing is positioned like this, right, then the area is not perpendicular to the magnetic field lines. What we mean by perpendicular would be if the thing actually was at a 90-degree to the magnetic field lines, but that's not the case. So for us to can consider this, we have to now use an adjustment or adjust our equation a bit to say that psi, which is your magnetic flux, is equal to the magnetic field lines B times the area times cos of the angle between the area and the magnetic flux density, right? So we'll use those equations as we go along, right? But it's another thing that we must know, is what we call the magnetic flux linkage. Magnetic flux linkage. This is um, more associated with coils. So when you talk about the solenoid and so forth, it's more associated with solenoids. So it says that let's say we have our flux line passing through a coil, right, of n number of turns, then the flux linkage through the coil is now given by this, right? The flux linkage is now given by this information to say B, which is your magnetic flux density times the area times n cos of theta, right? Where n is the number of turns. So if we have a coil that have several wires wrapped around it, then if we want to find the magnetic field or the magnetic flux lines or the magnetic flux passing, no, not that, but if we want to find the magnetic flux, right, in a sense we have to find the magnetic flux linkage, which is basically the same thing, but it's just that we are taking into account all of the area, all of the number of plates, not plates, but all of the number of coils that essentially are being, within that magnetic field, so to speak. So to find that magnetic flux linkage, then you just make, reference to this. Let me just check here. Let me give me a second. Um, yeah. So in essence, from a definition standpoint, you see, from a definition standpoint, magnetic flux is a measure of the flux. Let me say it again. Magnetic flux linkage is a measure of the flux in a whole solenoid or a coil, and so is the sum of the magnetic flux through each coil or through each turn of the coil. So to come up with a symbol for magnetic flux linkage, we just use the symbol for magnetic flux times n, right? Where n speaks to the number of turns. So if you were to find the magnetic flux linkage, then you're just literally saying magnetic flux by n, and obviously that is equal to, B times A times n cos of theta, depending on if the magnetic field lines are at an angle, to the area. Okay. So there's no difference. The units are also the same. They're also Webers. All right. So just be mindful of that, that they are all the same units. So imagine that we have an area here and we have magnetic field line passing through it perfectly. Then our flux is obviously equal to B, which is the magnetic flux, times the area, right? And if now we have a coil, then all we're doing now is basically counting the number of coils and timesing that by the flux linkage, timesing that by the magnetic flux, my bad. So N times B times A will tell us my magnetic flux linkage, or you could say, if I know the magnetic flux through one area of a coil and I know the total number of coils, then I just add them together to essentially find out the magnetic flux linkage. Here's just a simple question. It says that a circular loop of conductor of diameter 5 centimeters is placed at a right angle, right, to a uniform magnetic field with B equals 0.05 T. It says calculate the magnetic flux, right? Um, through the coil. So imagine that we have a coil, right? And our magnetic field lines, they are passing completely through the field lines. Okay. We know the magnitude of the magnetic field lines, which is B is equal to 0.05 Tesla. And of course, we can find the area of a circular loop. Area of a circular loop is pi r squared, right? So, and we're given the diameter in centimeters. So we know diameter, right, is equal to 2r, of course. So if I want to find r, then I'll say that r is equal to diameter by 2. So in essence, we could work it out to say that r is equal to 5 centimeters divided by 2 centimeters, which gives us 2.5. And we need to convert this into meters. So we say times 10 to the 2 meters. So if we go now and put this in a calculation here, pi, we know pi, you can just use your calculators, times the radius square. So that is 2.5 times 10 to the 2 square. And we can put meters in the bracket as well to show that it's going to square. So with all of this, we can see that the area is going to work out to be 1.96 times 10 to the 3 meter squared. Now we're trying to find the magnetic flux, right? Where we say psi is equal to B times A. So we have every information now. We have B, which is 0.05, times the area, which is 1.96 times 10 to the minus 3. Then from here and then, we can find, the overall magnetic flux. So when we do work out that, we're getting that the magnetic flux is 9.8 times 10 to the 5 Tesla, right? And from that now, so that's where we would have stopped, right, for that particular question. But the question continues to say that the plane of the loop is now rotating until the angle between the normal to the plane and the field is now 60 degrees. It says calculate the new value of the flux through the coil. So there's a shift, right? And once there's a shift, then we expect that the less field lines are going to pass through. So we could almost look at it to say that this is the 60 degree that the thing has shifted, right? So less field lines will through pass through the area. You understand? Less field lines will kind of pass through it. So with that being said, we now have to make an adjustment here to our equation. So psi is equal to b times a times cos theta. We worked out what BA is already, which is 9.8 times 10 to the minus 5 times cos of 60. When we go ahead and put that in our calculators, we're seeing that our magnetic flux is now going to be pretty much half of what it was initially. So 4.9 times 10 to the 5 Weber. Let me just correct something here. This is not Tesla. This is Weber, right? So that is pretty much what is talked about here. That's what we just using that equation. I'm going to pause the video here, and we're going to pick up in subsequent videos.